So hello again and welcome to launch webinar for CENOS radio frequency software version 2.0. My name is Michał Szczepanskis. I'm CEO and founder of CENOS company. I'm PhD in applied physics myself. So I have experience doing simulation in different software for more than 10 years myself. And that's why I'm very proud, really, very excited and proud to present you this new software version. I'm really proud to do that because well, I did the test myself yesterday, and I was really excited. So how easy it is to use it, comparison of my previous experience. So in the few minutes, we are going to make demonstration on the software. Then after that, there will be questions and answers. So please just wait for that. I'm sure you will have questions, and we will be happy to answer them. But before it starts, I have to do two things. First of all, I really would like to say thank you for those who are already our customers, subscribers. You trusted our software early on. We launched antenna design software earlier last year. But it was focused for antenna design, and now we are relaunching the software version 2.0, and we also rebrand that for radio frequency, which highlight incremental increase of the cases we can cover with that software. So now we can do all radio frequency related analysis, or at least major part of it. So that's why thank you again for those who are already with us using the software, and very welcome others to make your own decision after this webinar later. So before we go to the presentation itself, I want just to let you know who is our team. So the company CENOS is now 35 people. We have two offices. In our headquarters in Riga, Latvia, mostly covering European market, and we have second office in Mexico, in Querétaro City, which support North American market. And I want to show you the people behind the software, or at least those few guys you will closely work with. So, okay, just let me make full screen quickly. Apostolos on the left, Apostolos is our product manager, so who managed radio frequency product. Rainer is our lead simulation engineer who will lead engineering support in Europe. Bricia is our lead simulation engineer in Mexico. She will lead our support in North America. And Sandis is a product engineer for radio frequency product. So further, you will work with these guys. So that's why I just said that it will be very nice that you see their faces. Today, software presentation will be led by Rainer, and later all other guys will join for the Q&A session. All right. I don't want to let you wait anymore. I'm excited myself to see the software presentation. I hope you are as well. So that's why I want to give the mic to Rainer, lead simulation engineer in Europe. Rainer, please just take from here, share your screen, and show how CENOS radio frequency version 2.0 look like.
Okay, thank you for the introduction. Hopefully you can hear me all right, and you can see the shared screen as well. And so yeah, again, thank you for the introduction. My name is Reiners. I'm a support engineer here in Riga at CENOS. And basically, let's just jump right into the presentation. So, as you can see here, this is the initial boot up screen of Radio Frequency 2.0. And basically, you can design your RF model in any CAD software of your choice and validate it with CENOS. The validation process consists of mainly three general steps, which is the geometry definition and role assignment. The second one is the physical settings. And the last one is the result analysis. There's a fourth and optional step, which is the meshing, as CENOS generates the mesh for your model automatically. And so let's validate an antenna design. So for this presentation, I've decided to use the from CAD approach, which means that I'm going to be importing a CAD model that I've created beforehand and basically just simulate it. So I just clicked the from CAD, and now all I have to do is just import the model into CENOS. To do so, we have to click the folder icon that is pulsating on the from CAD button. So let me open that right now. I'm going to use this step file. And the first thing that CENOS asks us to do is if we want to create an automatic care domain, to which I'm going to say yes. So next up, we're greeted by the geometry application type screen. As you can see, CENOS now has more predefined application types, but these are not the limit of RF 2.0. So you're able to simulate anything you want with custom. So primarily we have defined 5 predefined application types. The first one being microstrip/PCB. The second one is wire antennas. The third one are reflector and dish antennas. The next one is multi-port networks. And last but not least, waveguides. So the model that I've chosen is an IFA antenna, which falls into the microstrip/PCB category. So let me just click that. And now we're greeted by the role assignment stage. The first thing that CENOS asks us to assign is the substrate. So let me click on that role. And now it's going to ask me to assign a volume for the substrate. In this model, we only have the one volume, which is the basic PCB. To assign it, we just have to click in the preview. It gets clicked on the volumes tab on the right side as well. And then just click assign substrate. It's really that easy. Next up is the patch. In this model, we defined the patch to be a 2D face on the substrate. And to select that face, we have to head into the Faces tab and select the F, the patch. Select that in the preview. It turns blue. Then press Assign Patch. Same goes for the ground. We click on ground, assign the 2D face that I've defined previously as the ground, click, and assign ground. It's really that simple. Next up is the port definition. So we've introduced the point-based port definitions, which make the port definitions infinitely easy. All we have to do is select the role. It asks us to click in the preview to select 2 points. Let me pan over to the place I want to select the ports. And then I just assign point 1 and point 2. So I selected the 2 points between which the voltage will be applied. And now basically the model is ready. But if I did have a much more complex model, such as I'd have another substrate with its own patch and ground here as well, I could just add additional roles with the add substrate, add patch, and so on. If I had a multi-port network, I could just add a second port as well and define it like such as well. We also introduced lumped elements. So basically the same way that we defined the port, we could just select two different points on the model and assign resistance, inductance, or capacitance to those 2 points just by clicking Add Lumped Element. And so, since this model is quite basic, I've already defined everything, and now we can just head on over to the physical settings stage. To do so, we just click Go to Physics. And now, in the physical settings, the first thing we are greeted by is the Simulation Control tab. Here, we select the frequency in which we want to simulate. So we are able to simulate in a single frequency, or we can define a frequency sweep as well. In this case, I'm going to select 2100 megahertz as the starting frequency and 24 megahertz as the end frequency. And for the frequency step, I'm going to select 100 megahertz. Here you can also see a switch that says Simultaneous Excitation. So if I had created a model that included more than one port, I could decide to enable simultaneous or sequential excitation of the ports. But in this case, I only have the one, so I'll leave that as is. Over on the next tab, we see the substrate, and we have to assign the material for that volume. So CENOS already has quite a few materials defined from which you can choose from. You can also create new materials by clicking on New, creating a name for it, and assigning parameters such as the dielectric constant and the dielectric loss tangent. In this case, I'm going to select the predefined FR4 as it suits my needs just fine. So I select the FR4 and then press Apply. So now I have pretty much defined everything in the model. So we also see two other tabs here called Ground and Patch. These are already predefined as perfect electric conductor, and we really don't need to do anything here unless we want to simulate using real materials. To do so, we just open the drop-down tab, select conductor, and here we can also assign the ground to be, let's say, copper. And then we would simulate using real materials. In this case, I'll keep both the ground and the patch as a perfect electric conductor. In the last tab, we see the port. Here we already have automatically assigned the impedance for the port and the phase shift angle to be 0. But if you want to apply a phase shift, or if you have multiple ports and you want to simulate, say, phased arrays, you will be able to assign a phase shift angle for each port. And basically, the model is already done. So if I want to simulate right now, I can just click Run, and it's going to simulate the case. However, I did mention there is a fourth and optional step, which is meshing. And in this step, you're able to manipulate the automatic mesh to your needs. So basically, manual meshing. So let me showcase that quickly. So for starters, we're greeted with the bare model. And before we can actually do any manual meshing, all we have to do is just press Calculate Mesh. And it's going to create the automatic mesh for the model itself as well. As you can see, the mesh already took into account the roles that we assigned. So it meshed the patch finer and the edges to the ground as well. But if I want to add another refinement, I can just disable the automatic meshing. And now we can head into the submesh for the substrate. And here we can select whether or not we want to select individual faces which we want to mesh finer, or we can select another edge. We can select the edge selection and assign more edges that I want to refine more finely. We can also already see the characteristics that the automatic mesher has already applied. So in this case, I think the model looks quite good. So I'm not going to do any manual meshing. And right now, I'm just going to press Run the case. Before we can actually run the case, we have to save the case in order to save the results. So let me do so. Let me save this as 0_IFA webinar. Press Enter. And then it's going to run the case. So now we have about 1 or 2 minutes while the simulation finishes. So let me showcase another important feature of CENOS, which is the live support chat. So as Mikhail's already mentioned, we provide a live support chat so you can connect to our support engineers at any time. If you have any questions or need any help, you can just create a new topic and just write your initial message. So, hi, I need some help with my simulation, and send. You can also create screenshots and drop them right into the message as well. This is a screenshot. As we can see, Bricia has already answered, and we can just tell her that everything's fine. Everything is fine. Thank you. And now we can close the chat. So the results are about to be done. Looks like we also see that Bricia has mentioned something else. So everything's fine there. And so we have to wait a few more seconds until the results are prepared. So now it's starting our visualization tool, which is ParaView. It might take a little bit more time since I'm streaming this. So here we see the results. So the initial screen of ParaView shows us the radiation pattern of the antenna and the electric field distribution. On the next slide, we can also see the radiation pattern slices in polar and Cartesian plots. And on the last slide, we can see the frequency charts. So the S parameter chart, the voltage to standing wave ratio, the impedance characteristic graph, and the accepted power of the antenna. So let me showcase another great feature of CENOS. So let me close ParaView here, and let's generate a PDF report. So this is a handy feature that you can use to share the results of your simulation with a customer or a colleague, or maybe even a superior. And you can probably also store these in your own databases to showcase, to keep as results later on. So this is the antenna we just simulated. It shows all of the results that we saw before in ParaView. And here's the 3D far field as well. And so yeah, basically this is a quite simple case to simulate. And we have also prepared a few other cases that are more complex than this one. So let me open up one now. So first off, we have a circular patch antenna. As you can see, it has an SMA connector at the end as well. And since you already simulated this, I can just open up the results as well. So the same deal that we saw before, the radiation pattern, the electric field, and the frequency charts as well. So next up, let me close this up. Next up, we have a hairpin filter, so a multi-port network. We can take a look at them all here. Let me open up the results for it as well. In this case, since we used multiple ports, we just see the electric field for each individual port. So the first slide is port 1, and the second slide is port 2. So let me select the frequency that is. So here's the S parameter plot, and let me select the frequency, let's say about 3 gigahertz. And I can see the beautiful electric field distribution as well. So the next case that I want to show you is a parabolic reflector case. As you can see, there's a dish here and the patch antenna at the other end. And let me open up the results for that as well. So here we see a beautiful radiation pattern as well. Another case that we can showcase right now is a lot more complex than anything that we've shown before. So this is a 4-port phase-shifted patch array. Quite a beautiful design, if I say so myself. And let me open up the results for that as well. So each port has a different phase shift angle applied to it. And that is why we can see some beam steering as well. Here are the polar and the Cartesian slices of the radiation pattern. And here are the frequency charts as well. And last but not least, a placement study. So here's a drone controller that has a patch antenna placed on top of it. The base of the controller itself has been selected to be aluminum. And here are the results for the antenna. As you can see, the radiation pattern is really affected by the material of the object that it's placed on. So let's select a different frequency. You can see that the radiation pattern will change in a second. And here we can also see all the PDF reports for all the cases that I just showed you. Here's the hairpin filter with its coefficient charts. This is the patch array. And here's the IFA that I showed you before. So you can also take a look at the frequency charts. And so yeah, one thing that I did not mention is that we also provide the option to export your results as a CSV file. So you're able to manipulate the data in your app of choice. So you can plot your data however you want and compare it with your other results as well. So that is it on my part. I'm really hoping to see you as customers real soon. And thank you for listening.
Yeah, thank you, Rainer, for the presentation. Now let's open this webinar for the question and answers and overall discussion. I'm very eager to hear what you think, what the question you still have. Yeah, and any feedback also welcome. Please just either raise your hand or just go ahead and switch on your camera and say.
I'm sorry, I do not have camera. Can I ask a question?
Yeah, sure, no problem.
How to simulate the parameters changing in frequency of the substrate and materials?
So if you, okay, let me pick this question. Did I get correctly that you ask for the frequency dependent materials?
Yes.
Okay, currently the software do not support frequency dependent materials. Basically, you just need to change your, I mean, you can create multiple material instances in the library which reflect a different frequency, and then apply that for separate frequencies for separate simulations. So it just will be separate simulation for now. We do not have this function in library. However, we're already just aware of this, and it's in our roadmap.
There is some scripting language which can be used to start the simulation, load the simulation, and change the parameters of the materials.
You can prepare multiple cases, simulation cases, and run them in a batch with a script, like let's say overnight, for example. So you just prepare multiple cases in the evening, just run that script, and in the morning you will have all of them simulated. This is an option.
Okay, thank you.
Hello. I would have a question. My question would be if the software, the simulation software, would be also a possible good fit for checking the matching of the connectors and kind of making the design of the up to 44 or 67 gigahertz of connector footprint with the connector itself on the PCB.
Apostolos, don't you mind to take this question?
Yeah, sure. Yeah, absolutely. You can simulate things like this. You can model your connector and the PCB trace, for example, and you can see how it behaves at very high frequencies like 50 or 67 gigahertz. So yeah, CENOS allows you to do that as long as you can, import a model which has a connector and the trace, and yeah, you can absolutely simulate the scattering parameters, for example. You can visualize the electric field distribution. So yeah, you can absolutely do that.
All right, thank you.
So in general, software employs Fdm Engine. So that basically means there is not so much limitations for the software itself. So it's just cover the pretty huge part of the radio frequency design tasks, perhaps only excluding low frequency wire antenna where FEM is not really efficient. So I mean, it's still doable, but it's will be enormously long. But other than that, all patch antenna, all high frequency, really high frequency. High, I mean, above 100 megahertz for sure. So above 100 megahertz, there's no problem at all. I also saw one message in our in the chat here. So I would like to thank Simon Merritt, who is our customer. He just wrote that I have to say, as a customer, the support team is amazing. Thank you, Simon, for this, but I cannot resist from quoting you here.
I would like to ask about the results of the simulation and the truth of that about antennas that are simulated. How you compare the results from the simulations and the measurements of the antennas?
Gatis, thank you for the question. That's absolutely legit question. Yes, we did comparison both with the real field experiments and with other software available in the market. Actually, just to be honest, that comparison with other software had been done not by ourselves, but actually our users and customers did that. We also allow academic users and hobbyists to use our software for free for non-commercial use only. And some of them did that comparison themselves, comparing, well, I would mention ANSYS HFSS, console, CST. This is, yeah, at least this is what I know. They did comparison. We even published one blog post. I can just show you later, where one of our user did this comparison of his own, and actually the match is pretty good. We are pretty confident on the accuracy of the software. We also tailored automatic meshing algorithms in the way that it just created a reliable mesh. Although if there is something not catched by automatic meshing, user can always do manual meshing, which will adjust actually the results and ensure accurate results.
About the meshing, I know that there are some rules in the meshing that cells should not change very rapidly in the size. But on your in your presentation, I saw that the size of the mesh changes pretty rapidly there.
Guys, it definitely depends. Well, first of all, in the manual meshing, there is an option you can actually control the ratio. You can control how fastly they change. But automatic meshing is optimized. I would like to claim that this particular mesh was okay. So the result was good. However, of course, we optimize that in the way that we achieve results fast enough. Yeah.
About the engine itself, does it use only computer, only processor power, or it can use the GPUs too?
And so I will take this question as well. So current setup of the software is able to utilize all CPU you have, but there is no limitation. So for the GPU, of course, we use GPU in the post-processing, like analyzing the results and processing results. But for computing itself, we don't use CPU. Although I don't know if I will open the secret or not, but we actually have the R&D project in our team where the guys are working on GPU as well. I think we will come to that point later and sooner, probably not so fast. It's not like a matter of weeks, but this is like a R&D project. For now, CPU only.
Hello. I have a question. Does the software handle a reflector array of periodic structures? And the second one would be lenses. Can it handle lenses?
Bartos?
Yeah, this can take that. So yeah, for periodic structures, it depends on what kind of design you're looking at. If you want to design a phased array, yes, the answer is yes. We don't support periodic boundaries, if this is what you're referring to, but that's just a matter of speed up. So it doesn't really affect the results per se. As for lenses, yes, the software should be able to handle that. For example, you can model the electric lens in front of a microstrip antenna, and yeah, the waves should take their form from that lens.
So if you can handle lenses, then are you also saying you can handle radome materials, different radome materials?
Yeah, so for materials, as long as you can specify like the electric constant and so on, yeah, that should be fine.
But have you done some simulation work to prove the accuracy of that work?
We've run various tests on various structures from wire antennas to reflector antennas and to microstrip antennas, and the results do look accurate. We have not tried against lens antennas per se, but we don't have a particular reason to expect why the results would deviate much.
David, we are very welcome. So you're well welcome to test out, and we are very eager to cooperate with you to test out if you have any doubts around that. And by the way, let me ask you the question as well, if you don't mind. So you mentioned that periodic. Then you ask that. Do you mean the periodic boundary condition?
Well, yes and no. Reflector arrays are made out of periodic structures, right? So a lot of development work has been going on with using reflector arrays as a replacement for reflectors due to its compact sizing. And that seems to be a major goal of a lot of the designers in the future. A lot of software do not handle that very well, and they tend to do it very slowly if they do handle it. HFSS has done that a very good job of that, and I was just wondering how your software compares.
So good point. Well, no doubt, ANSYS HFSS is a great software. No doubt about that. Although pretty expensive as well. Thank you that raising this point. Just to repeat, in general, there is no limitation on any kind of geometries here. Although, of course, we're constantly looking for the way to speed up calculation in some particular cases. And in this case, we might consider to introduce that symmetry boundary condition. Actually, we have that symmetry boundary condition in other applications we support. So not radio frequency, but actually we have also software for low frequency in the market, induction heating, particular, which is also well recognized by the market already. And there is symmetry boundary condition there. I guess we might. Well, let me write down and include that in our roadmap for investigation. But I don't think there is a big issue to work on that. But thank you for the raising.
Thank you for answering.
Do you have a plan to when add the time simulation to your software time domain?
So the best way I would call our head of our R&D is not here, but I can answer myself in the way that I know that we have had this discussion. Basically, the engine we use now is Fdm engine, which is pretty robust, and it's good for big models, for complicated models, including some placement studies, And this is the reason why we went this direction. For time domain, we are aware. We even know the engines who can support that. Nevertheless, we just didn't have that included yet, and I guess we don't have that in the near future because we don't see like the huge value. However, I'm pretty open to discussion around that. By the way, if you can specify what kind of application you intend to simulate with this method, we can take a look how we can treat that. Could you just tell more about the application you want to do?
The pulse radar, for example.
Sorry, could you repeat?
The pulse radar.
Okay, radars. Yeah, okay. This is something that we do not support much because we don't have this time domain. Okay, so thank you. I will write down, and we will consider that in our R&D meeting. Yeah, this is the only thing I can tell you now.
Thank you. I'm sorry, I'm still asking questions. Can you call the requirements for the memory? For example, how much memory we have to have for 1 million elements of the mesh?
Of course, it depends. So it depends on the size of the case you have. Yeah, the bigger model you want to simulate, the more RAM you need to have. The more, the better. There's no limit actually.
Yeah.
But regarding the particular requirements, I probably would ask writers to pick up the question and just share the best practice we have so far. or Rainer, are you able to answer? If not, then probably Apostles may.
I really don't have any exact values to specify. I've had cases running on low memory, such as 16 gigabytes of RAM, and they're doing just fine. But a million sounds like a lot, and I assume that having at least 64 would be good. But I assume they would also run on 32. But I don't have real exact numbers, and hopefully you don't quote me on this.
Well, so far the best practice is that I see that the majority of our customers are running simulation on 32 gigabytes machine. More rarely we see 64. We do not recommend to have 16 gigabytes. It just seems to limiting you. 32 is like the best way. Although we have also some champions who do even 124 gigabytes, or even more. I think the biggest I have seen is 400 gigabytes, but it's something very, very exotic, maybe. So there is one more question in the chat. Apostles, could you just take this?
Yeah. So from what I understand, if I understood correctly, what you're referring to is basically be able to add kind of a lumped element that is not as simple as RLC, although not 100% sure.
So sorry, just for everyone, just could you just brief the question itself and then answer?
Yeah, sure. Yeah, basically what he's asking, if I understood correctly, is whether you can add non-ideal matching components into the antenna and take them into account. You can do that as long as you have, for example, if you have the S parameters of this network, either as a TASM file or something, and you convert that into an RLC element. You can, of course, add it and basically have CENOS take it into account.
It's if you are not satisfied with this answer, just okay. Yeah, okay, thank you. Yeah, thank you for question as well. So if not more questions here, I really want to thank everybody for joining this webinar. I already want to announce the series of the following webinars. We probably will come up with the schedule and topics later on that will be focused on particular applications and some peculiarities of the software, just to help you to deal with that. I also cannot resist from the incentive to call to actually purchase now or sign up. You always can you can take free trial, or you can ask for the demo. We can even customize the demo for your particular application if you have any doubts about the software capability to work with your particular application. But other than that, I'm really excited to present you the software which we designed to be affordable and easy to use for every engineer. So we hope we cover the major part of radio frequency applications, and we did our best to make the process so easy that even newcomer can do that. So you don't need to focus on numerics or in simulation anymore, but you can just quickly do your simulation and focus on actually design where you are the best, right? So I really want to encourage you to try out and to subscribe if any question, please ping me personally or anybody from the guys I presented, and also our sales team is pretty eager to jump in a call with you and learn more about your particular application and needs and see if we can satisfy them. Thank you very much for joining this webinar again, and hope to see you soon. Bye-bye.